Welcome. My name is Patrick Curran, and along with my friend Greg Hancock, we make up Quantitude. We're a podcast dedicated to all things quantitative, ranging from the relevant to the completely irrelevant. In today's episode, we explore a variety of issues related to model evaluation and fit. We also discuss compulsive counting, mashed potatoes, letting the horses out of the barn, building Model 747s, Jenga, Moses' third tablet, the Pirate Code, demon conferences, and Roo Mates. We hope you enjoy today's episode.
All right, my friend, I've been thinking about something. You ready for my thoughts?
I am always ready for your thoughts.
Okay. When you talk to people about what careers they choose, they'll often cite some sort of childhood thing that sent them on that direction. You might talk to someone who's a social worker, and they'll say something about, well, I had some hardships as a kid and it really motivated me, as an adult. Or research physician, maybe had a parent die of something and it sort of set them. And so I got to thinking, even though there's no path to our field, there's really no path, as we've talked about, right? No one chooses statistics. Statistics chooses you. But I was thinking, is there anything about me and you as kids that would have made this click for us? And so I'm going to ask you, was there anything that might have made quantitative stuff click for you as a kid? Because you were a cop, right? You're going to be a cop.
Yeah, I am arguably the least motivating story for going in the field as you could get. Is the short answer is no, there was nothing. For whatever reason, I wanted to be a cop, and I did when I was 5 years old, but it just kind of stuck with me. I mean, it was all the way up to kind of 18, and the only reason I went to college was to kill time before I could do that. So I am breathtakingly uninspiring, as there is no story, no nothing.
I bet that's not true, and here's why I say that. Something about our field resonated with you. There's something about it that became more interesting than helping people. One thing, I've known you for a very long time, you count things, right? You list things. You will say, there are 3 things you got to know. You do this frequently.
I am a compulsive counter, and I'll tell you 4 reasons why that is.
Yeah, but were you always like that?
I don't remember.
That's what I wonder about. That's why, if the little Patrick Curran running around having to count everything or label things or make order of things, that's really more what I was wondering about.
No, I was not organized. I was not structured. I didn't count in my own head.
As we've talked about, I had this happened to me, and you can go back and maybe pick some things that made it align, but I absolutely not only was a counter as a kid, I am still a counter. I cannot go up or down stairs without counting the stairs. If I'm actively involved in a conversation with somebody going up or down the stairs, it's a really difficult conversation for me to have because I'm trying to process the number of steps that we're going up or down. I just counted everywhere. And if I did something with my right hand as a kid, I had to go do it with my left hand. So I'm actually quite ambidextrous in a lot of things because I couldn't handle the asymmetry of not doing something. Even the number of deodorant strokes I put on every day has to be a multiple of 13. And I don't know what that means, except that I am unusually fresh. But it's like if I accidentally go to 14 on one side, it's like, no, I'll be leaning over the whole day. I'll be tipped over. So I got to make sure I bust that up to 26. I wonder if any of this was so ingrained in me as a kid that when I finally encountered this subject matter, there was this click. And this is me retrospectively telling this story about liking order, liking counting, liking numbers, liking symmetry.
Okay, now you didn't raise symmetry. You were asking about counting and order.
Okay.
I do the cooking at home, and a while back I made a big pan of mashed potatoes, and with some fanfare I put it out on the table, and it was like a skating rink. It was smooth and even and perfectly balanced. And I put a spoon right on top. And as my wife walked by, she picked it up and went, and dug it all up. Like, your deodorant thing is totally weird. Like, totally weird. But symmetry is fine. All right, so leave symmetry alone.
Okay, understood.
All right, I love your stories. What's your point?
Well, all right, I'll make a point out of this. All right, you ready?
I am.
Here comes a point and point coming at you.
There aren't 3 points?
One.
There we go.
I thought. 2, that statistics. 3 was an ordered place. One of the things that I think that I really liked about statistics was it was trying to bring order to things that otherwise had the appearance of chaos. And I do like structure and I do like rules. And the funny thing is that I've learned the more statistics you learn, the deeper you get into it, the more you realize that very few of those rules really apply. That has been a very eye-opening experience for me. In fact, early on, we often teach things. These are the steps you go through for hypothesis testing. These are the guidelines that we have to retain or reject. And then you go on in your coursework and you go, yeah, there are other ways to think about it. And that has been very eye-opening for me, just to find out what an open space statistics actually is in its practice. I don't know if you've experienced that.
I couldn't agree more. And in my own teaching, I kind of have a standard joke of, if you ever meet somebody and they say, you know what I love about statistics is how objective it is. And the general rule is, if anyone ever says that to you, they don't know anything about statistics.
Absolutely.
It dovetails with the old joke that people go into statistics who are bad at math. It's the same kind of thing. I was horrible at math. But when I don't have to have an exact solution, when I am trying to build a case to understand the complexities of a set of data, I'm in my element. Dan Bauer and I were working on a project once, and I was out of town, and we were going back and forth over email, and we were computing derivatives of this nonlinear trajectory. And we kept coming up with different derivatives, different solutions. Dan's would always be the same, and mine would be different. And so finally, Dan, being the consummate teacher, said, well, here's how I did mine. And he said, first I used the chain rule, then I used the power rule, then I gathered these terms, and then this. And he said, so what are you doing? And I wrote back and I said, I typed Control E for evaluate, because I was using the LaTeX math editor. And I was trying to guess where the parentheses would go. And so I'd move the parentheses and do Control E, and move the parentheses and do Control E. And so I just wrote back and I said, I hit Control E. And Dan emailed back and he said, I think I found the problem.
Right.
So, yes, we navigate waters that are more art than anything. I believe, in being a good quantitative methodologist. It is as subjective as is reasonably imaginable, and I think we do this field a disservice if we don't embrace that, right? Because it's not an objective. It's not rule-bound. It's not that you just do these things and there are a series of go, no-go gates that we go through. I think poor quantitative methodology is done when you're trying to follow those go, no-go gates.
One of the ways I try to frame this, and my intro classes are always funny because so much more that is down the road, and you have to decide, do I start them off in a very contained world and peel back the layers as they get farther on, or do I tell them what a circus it is on day one? And the answer is no, I don't. I might allude to the circus from time to time, but I talk about, typical prescriptions, but most of what I say, I try to imply that there's a plus or minus 2 around it, a little bit of fuzz. But one of the ways that I hint at this idea of uncertainty is when I talk about different statistical techniques, I try to also talk about the model. that goes with it. And, from the very first hypothesis tests that we do, however you want to think about hypothesis tests, I also try to talk about it as a way of explaining or thinking about the way the world works. And I try not to get too light a candle and incensey about it. But I do want people to think that every test that we're doing corresponds to the assessment of some particular model. And I don't know if you start them off that way or how you deal with that.
You raised a really good point, because it's overwhelming in an intro stat class to think about all the complexities that you're eventually going to have to deal with. And so how I approach things in, say, an undergrad intro class versus an advanced grad class are very different.
Yeah. So when I get to my structural equation modeling class, for example, and maybe we can do a little bit of ramp up to that. But when I'm there and I talk about how we think about things, how we frame models and all of that, people will invariably say, why didn't you do this in the first class? And I always hear in the back of my mind, Jack Nicholson and A Few Good Men. It's like, you want the truth? You can't handle the truth.
You want answers? I think I'm entitled. You want answers? I want the truth. You can't handle the truth.
And I just think about, when there are these creatures that have just, stepped foot on the statistical earth, and I don't know that I want to expose them to the complete chaos that there is. But so I do it gently, and by the time we get to that later class, I think the conversation makes a bit more sense. But, what I'd like to do, if it's okay with you, is think about things a bit from a model perspective. In particular, maybe talk about how we think about the evaluation of our models, and all the way back from the beginning, but maybe moving it into structural equation modeling, where we tend to hover around covariance structures and mean structures. How does that sound
good.
For you today? Well, go ahead, do it then. Pop quiz, go.
Wait. I thought we established I could only do this to you.
I don't remember that. Go ahead. So get us there. Work us up. Do it.
I will throw a little rant if you say all models are wrong.
Are those the ground rules?
It's a pet peeve. And the reason it's a pet peeve is sometimes this is announced with like some great fanfare, right? That's your model, but all models are wrong. And just what drives me a little crazy is that's what a model is, right? That's the definition of a model. A model in some way you can define as a simplification of a more complex reality, right? And as soon as we start thinking about that, think about like a highway map that's in your glove box. Well, for those of you who are our age and used to have highway maps, a map is a model. There's a great Cormac McCarthy book where he has this preface where he talks about how a king wanted a truly accurate map, and the only way they could do it was to make it life-size. And so it was a life-size map of the kingdom, and that's the only way it's not a model, right? So if I sit in my basement and put on a fire and put on some Miles Davis and work on a Model 747, and then on Monday at 8 a.m. fly 382 people to Charles de Gaulle Airport, it's not a Model 747. It is a 747. It's a model I build in my basement because it's a simplification. So we start right out of the gate that a model is some attempt to understand a more complicated system using a simpler framework, a summary framework. And then we're off to the races, which is so much fun about our job, which is we want to simplify, but we don't want to oversimplify. So how do we find that balance where we can build an accurate representation of what we believe to be a more complicated system, but that still maintains fidelity to the characteristics of the empirical data that we observed? I guess maybe that would be my ground ball I would hit into play, which is right out of the gate, we're trying to build a model that is fitted to our observed data that we know to some degree to be incorrect, but we have to make an empirically and theoretically informed determination as to whether we believe the extent to which we are wrong is acceptable, or that we have made errors somewhere in the body of our model that would question the internal and external validity of the findings.
So I like all of that. let me bypass the models at like the t-test level, but let me go to multiple regression if that's okay. And just imagine a multiple regression model, however many predictors that you want. Can you talk about that as a model and how you think about that from a fit perspective?
You really are making this pop quizzy.
Oh, do you?
No, I'll give it a go.
If you don't think you can do it, that's fine.
I don't, so maybe you should. I mean, I have a two-bit opinion. A multiple regression can be equivalently defined as a structural equation model. It is a model in the sense that you are expressing the conditional distribution of a dependent variable as a function of an optimal linear combination of your set of predictors. I do not consider that a model from an a priori theory testing perspective because you've imposed no restrictions on it. If you estimate a multiple regression model as an SEM, it has 0 degrees of freedom and it perfectly reproduces the covariance matrix and mean vector that were observed in the sample. And the reason is all variables are allowed to relate to all other variables. All IVs predict the DV and all IVs correlate with one another, and so you've imposed no restrictions. Sometimes I teach about how degrees of freedom are a numerical measure of your courage. So I'm in North Carolina. We have tall trees. In my backyard, I have a bird feeder, and it's like 10 feet off the ground because that's as high as I could go on the ladder. The ladder went twice as high, and I got up to about 10 feet and was like, okay, I'm done. This is where it goes. That's my numerical measure of courage, but degrees of freedom are numerical measures of courage because each degree of freedom you have represents a restriction that you've imposed on the model. Often we remove a parameter. Sometimes we'll set them to be equal. There are various things that we can do. I don't know if this answers your question or not. I guess in a strictest sense, I do not view a multiple regression model as a structured model that we're imposing restrictions on to test a hypothesis. I view it as kind of throwing the barn door open and just letting the horses out and see where they go.
Yeah, it's a funny model. I think that the regression model is this really nice pivot point between two worlds. And if you talk to someone who has training up through multiple regression, they might say things like, the fit of my regression wasn't that great. You say, oh, well, and what do you mean by that? Of course, you know what they mean by that. And they say, well, I had an R squared that was only 0.1 or 0.2. And that's how they characterize fit in a multiple regression. It's all localized to how much variance is explained in a dependent variable. That is fit within that world. If you talk about structural equation modeling and take the exact same model, I think there's an important distinction between the two from a psychological commitment standpoint, maybe, in that if someone has a theory that says there are these 3 variables that ought to exert an influence on a particular dependent variable, and yes, I have accounted for other things that are relevant in this world, this is the system that I'm committing to. Now we tell that person that it's going to fit perfectly and by default, right? And I love having this conversation with somebody. It's not just this type of model, but when someone comes into my office and they show me a picture, even more complex than this, and I can tell that it's a just identified model, I love to do this thing where I go, I predict that your model is going to fit perfectly. Like, really? No way. Seriously? I am almost, in fact, I am positive it is going to fit perfectly.
Okay, this is why so many complaints are filed against you. But go ahead.
That's the reason. Yeah. Okay. So, but then, I talk about degrees of freedom and how things are connected, and that we now think about model fit differently, and that it's not a very courageous model as you would describe. And that's because we shift what we mean from explaining variance, which is the way we talk about fit in the regression world, to the fit of a system as a whole. How well does this system account for all the variances and covariances and probably the underlying mean structure too of all of these variables? And the answer is perfectly, because everything is hooked up to everything else. And that's one of the hardest things that people have. They come into my class having had regression, and they think about fit always in terms of the variance that's explained in a particular variable. And I say, well, in this model, all the variance in y is explained, because this error term is a part of the model. So our goal isn't, about the explanation of variance of one particular variable absent error. It is understanding how all of these things relate, and you have done nothing to challenge their ability to relate. And so in that sense, I talk about degrees of freedom, and then people will often say things like, so should I take out some paths, or should I change it? And my answer is, well, not unless you believe that that is a reasonable competing model. And then maybe you do articulate multiple models. But that starts to put us in this world of fit when we can't sort of rub our temples and say, oh, it's going to be perfect, right? We move into this world where we try to assess the fit of models, whether they're as simple as little measured variable path models, or if they're the giant, multi-time point growth, multiple indicator, time-dependent covariates. Assessing the fit of something like that, it's a very challenging world that people enter into. What I tell people is that you guys are too accustomed to having the p-values do the thinking for you. And that's what happens when you come out of a hypothesis testing world, that people are like, oh, I didn't make it. Didn't get under 0.05 or whatever. It's like, okay, we get to this world and all of a sudden there's this lovely old phrase that, the person with one watch always knows what time it is. The person with two watches never knows what time it is. And we usher people into this world of models and fit and degrees of freedom. And it is tough. It's different for them. I don't know if you experience that transition with people.
Oh, absolutely. And the difficulty I often see is the opposite side of the p-value, which is you estimate a path model, you impose restrictions, there are degrees of freedom. Every parameter is highly significant, and the model is a freaking train wreck.
Right.
I find that more challenging because a student will say, but every predictor is significant. It's our own fault, right? Because we train them to think about significance and non-significance and R-square in earlier classes. And then we chastise them for being so focused on significance and non-significance in R-squared.
It's kind of fun, actually.
Yeah, tough crap. I mean, we get paid like minimum wage in this job. We've got to derive enjoyment somehow. You know how I view it? My entire life is governed by analogies, and I realize they get tiresome sometimes, but, they work for me. I picture everything that we do in multivariate statistics as a game of Jenga. Is that the one, the tower, where you have the blocks?
It is.
That's your saturated model. You're imposing no restrictions. You're estimating every parameter that can be estimated. And so a multiple regression model is saturated. All variables relate with all other variables, and you've imposed no restrictions. And we have an observed covariance matrix and mean vector, and we have a covariance matrix and mean vector that is imposed by the model, that is the associated predicted covariance matrix and mean vector. When a model is saturated, by definition, those are the same, because you've imposed no restrictions. So that's your Jenga tower. What we start doing is to say, all right, if the goal of multivariate statistics is data reduction, you can sometimes think about that as, can we reduce the parameter space to get a simpler representation of what we believe to exist without doing harm to the data? All right, and so harm is going to be measured in, we have observed covariance matrix and mean vector, and we have a reproduced covariance and mean vector. When we impose a restriction, those two are not going to be the same anymore. They're going to be a little bit different, but now the fun starts, because now it's, well, how different can they be before we start to worry that we don't have the right restrictions? And that's the Jenga game, because you start putting in these restrictions and you start pulling out a block. And the tower stands, and you pull out another block, and the tower stands, and you pull out another block. But at some point, that tower is going to come tumbling down because it's no longer structurally sound to be able to stand on its own. And so I just characterize the last 30 years of my life as a child's game. I'm going to take a moment now, so go ahead and you can talk for a while.
Now I'm thinking about like Candyland and pickup sticks and all these other things.
Don't trivialize our career, okay?
Okay. So I'm totally distracted by the fact that you chose Jenga as an example. You and I have never talked about this before. And a couple of years ago, I gave a talk called 7 Dirty Secrets of Structural Equation Modeling. And the theme picture throughout was the most insane Jenga tower you could ever see resting on one bar at the bottom. Right? I mean,
I had no idea.
So, yeah, that's right. So it's one of those other spooky separated at birth parallels. But absolutely, that's, that is a way to think about it. As long as you are, I would say, taking the bars out before you get to the data, right? Because I like to think about this as a confirmatory process. So you decide which bars you don't need in there, and then you get the data and you go, oh, it collapsed or it didn't. One of the things I want to steer us toward is that how we measure whether or not it has collapsed. Throughout our whole statistical lives, we talk about, at least I like to think about it this way, we have what we observe, we have what we expect. And from the very first time we formally encounter observed and expected is in a frequency setting, right? We explicitly, I can picture the columns that we have of frequencies we observe, frequencies we expect. And it's always frequencies we expect based on a model. And that, for me anyway, is the first introduction that I have with students to chi-square as a way to formalize the comparison of observed and expected. Well, this world also has observed and expected. It has the observed variance, covariance matrix, and mean vector. And then it has what we expect based on our model. And so in comes the chi-square. Chi-square. Are you loving the chi-square or are you hating the chi-square?
I have concerns about chi-square. It's like the guy at the party who's like totally cool and well-dressed and is really funny and people are gathered around him and you're sitting over to the side saying, he's not all that. So go ahead.
Wait, okay. So chi-square is the very well-appointed gentleman at the party that people are all gathering around?
Who's all surface. Yeah.
Okay. Okay. So there are a lot of problems with the chi-square, I think. And it's funny, chi-square used to be really the go-to measure of data model fit for things. And it's a very natural way to come out of the whole observed and expected world that you have a chi-square representing it. But a statistical test isn't really the same thing as assessing goodness of fit, I think. It's a formal test of fit, but it's not exactly the same as an assessment of practical fit. And one of the problems with chi-square, first of all, is that the whole logic of it is completely backwards for our purposes here, right? A lot of times when we encounter chi-square or other test statistics, we're looking to reject. In this world, it's exactly the opposite, right? You've articulated a model that you feel like your career hinges upon you not rejecting it and wanting to retain it in the end. So in that sense, chi-square is kind of a very funny thing to bring to the table because your motivation, of course, should be truth, but really what you're hoping for is that chi-square comes out to be something really small. And one way that chi-square can be really small is if you got a great model. Another way, for example, is if you've got a tiny little sample size. So the whole logic of really wanting to see if the data that are observed and what you would have expected are close, it's odd. It goes against what we have encountered sort of up to this point in our statistical training. And so people invariably will get significant chi-squares, but that still used to be the fit index of the day, right? That used to be all there was. And some people still cling to that guy who seems to be charming with all the people gathered around him.
Being the total hypocrite that I am, I feel like a chi-square and an SEM should always be presented to the reader. We'll get to this in a little bit in terms of, what information do you provide in support of your model. Despite all my concerns, and I share them with you as well, it is a critically important part of the model. And so just to clarify very briefly where the chi-square comes from is you've got some system of variables. So just for simplification is let's say that we have 10 manifest variables spread out left to right in some kind of mediating model. All right, so some work I do is looking at the intergenerational transmission of parental alcoholism. And so you have, as a child of an alcoholic or not, yes or no, predicts environmental stress, predicts negative affectivity, predicts affiliations with deviant peers, and then predicts adolescent substance use. And then we also have parenting variables and temperament variables and all these things. we could allow all variables to correlate with all other variables. That's called a saturated model, right? So every variable gets a variance, every variable gets a covariance, every variable gets a mean. And we perfectly reproduce the covariance matrix and mean vector among those variables. And then we impose our hypothesized model into our system of variables, where hopefully we're putting theoretically motivated restrictions, where we say, okay, parental alcoholism only influences stress, that in turn influences negative affect and so on. We've imposed restrictions, and now we're going to get a difference in model fit. The chi-square represents the difference between the fit obtained under the saturated model and your hypothesized model. And so as Greg says, we have this back-asswards null hypothesis. Our premise is our model is right. Right? So the null hypothesis in SEM is the observed covariance matrix is equal to the model implied covariance. And then it's like being in a bar and throwing down with some drunk guy next to you is saying, okay, you have to bring evidence to say that I'm not right. Right? I mean, this is completely reversed from what we usually do. The typical null hypothesis is the treatment group and the control group are the same. Men and women are the same. And we have to bring empirical evidence to disprove that. Right? There's a whole books written on called The Black Swan, right? Is all swans are white. Well, that holds until you present a black swan. You bring empirical data to disprove the null. But we flip it around and say, okay, I'm going to start with my model's correct, and now the data has to prove me wrong. But as you noted, we can do that because we have very low power. The one that drives me a little crazy is we can do that by just throwing more parameters at it.
Sure.
Right? If we're cowardly and impose one restriction, the model's going to fit well. Why? Because we're a bunch of cowards. That's one reason, but there are a ton of other reasons, right? If the data is non-normal, it can inflate the chi-square. If we have a large sample size, so we're in this paradoxical thing where we need a large enough sample size where the asymptotic properties of maximum likelihood come on board, but the larger the sample size we have, the greater power we have to reject the null hypothesis based on trivial differences between the observed covariance matrix and the model implied. I think the chi-square is an important first step, but there are about 100 reasons why I couldn't care less what that p-value is. You have to bring other data to bear to convince me one way or the other how you're adjudicating your model.
So I like so much of what you said in there. Reporting the chi-square as a first step, yes. Bringing other evidence, I think about this in exactly the same way, that this really is, in the end, an evidentiary argument. And that's very frustrating for people. Where I said earlier that, the person with one watch knows what time it is, the person with multiple watches or two watches doesn't know what time it is. Structural equation modeling gave rise to this, it's like a cottage industry of fit indices that, really exploded in the 80s and 90s. And at some point, you could see reflected in software packages, you would get like 30 different fit indices where essentially the software was just saying, oh, hell, you pick, because there's so many there. There's a really cute quote by Yorskog, because Lisrel was the only structural equation modeling software packages for a very long time. And so they introduced fit indices, the GFI goodness of fit index and the adjusted goodness of fit index, which I prefer referring to the GFI as the goofy. When he was asked why they put that in there, because that was a whole new idea, his answer was, well, this is a quote, well, users threaten us, saying that they'll stop using Lisrel if it always produces such large chi-squares. So we had to invent something to make people happy. The GFI serves that purpose. But so that gave rise to, this whole collection of other ways of characterizing your model beyond a chi-square, trying to look at your model from different angles. And there really are a ton. I might ask you if you have some, and I'll be careful in my language maybe, I air quotes, favorite fit indices that might be alternatives to the chi-square, ones that you tend to eyeball more than others?
I have grown less enamored with fit indices as each year goes by. Very briefly, I mean, again, just to place it in context, is there are kind of two classes of fit indices you can have. Is they're incremental fit indices, and there are some that are absolute fit indices and some that are called relative fit indices. So we talked a couple of minutes ago about how the chi-square really is a likelihood ratio test between a saturated model where everything is allowed to correlate with everything else and your fitted model. Well, a fit index is kind of like that, in that instead of a saturated model, it's called a null baseline model. It's a ridiculous model, right? You want to compare it to something, right? That's the whole thing, is everything is relative. If you're ever going to talk about good or better or worse, you have to have something to compare it to. So the comparison is, at least for the classic baseline model, is, remember, we have our 10 manifest variables in our mediating model. The baseline model is you literally fit a model to a parameterization where each variable gets a mean and each variable gets a variance, but no variable is allowed to relate to any other variable. Mm-hmm. And then you're measuring the relative improvement in fit by allowing your variables to relate to one another.
Yeah, I have an analogy for this. That let me insert that right here, if I may. When we first bought the house that we live in now, we had these neighbors who had like knee-high grass and all kinds of just crap in their yard. I won't go so far as to say car parts, but there's a good chance there were parts of broken lawnmowers and other things. When I would come home, I would circle past that house and I would go, oh my God. And then I would pull up to my house and I would go, dang, this is a nice house. And I felt that way because I had just driven past that particular house. Yeah. To me, that's what incremental fit indices are, that someone decided what the universal ugly house is, and they make us drive past it so that we can be super impressed with the house that we live in. Now, unfortunately, we now have meticulous neighbors. And I know, I drive past their house and I go, wow. And then I get to my house like, eh.
Yeah. My version of that is I was in an athletic event and got put in a younger age group and I lost, and the winner came up to me and rapped me on the shoulder and said, "You did great for an old guy." So we have this, and there are some programs that, for the baseline, they allow what will be the predictor variables to correlate with one another, and so and other programs don't. It is difficult. It goes back to your 2-watch analogy. Mm-hmm. Dan Bauer and I do some teaching, and we do the same example across multiple software packages, and everyone has a different chi-square and different fit indices, and you want to gouge your eyes out. Going back to the incremental fit index. Oh, there are a zillion of them, but the Tucker-Lewis, the comparative fit index, the incremental fit index, all of these are the kind of the standard ones. Well, at least back in the day, as you looked for values exceeding 0.9 to indicate good fit. But remember, never go back and read classic papers. So Bentler and Bonnet is one of the highest cited papers. I don't have it in front of me. I'm paraphrasing my memory on it. But my recollection is where they introduced what would become the comparative fit index, that Bentler made the comment that in their experience, models that obtain values less than 0.9 could be improved upon. All right, so think about that for a moment, right? Mm-hmm. They didn't say models above 0.9 were adequate. They said models below 0.9 could be improved upon, yet Moses now has a third tablet that says fit indices shall exceed 0.9. Mm-hmm. And then there's recent work that says, no, 0.9 is totally unsupported. It should be 0.95. It's like, okay. So we have those incremental fit indices. And then there's a class called absolute fit indices that doesn't use a baseline model. And there are advantages to this. The big one in town is the RMSEA. That is a really nice per degree of freedom measure of misfit. The null hypothesis, for a properly specified model, the chi-square follows what's called a central chi-square distribution. And then if a model is misspecified in some way, it shifts that distribution to be what's called the non-central distribution. And the difference between the peaks of those is the non-centrality parameter. And actually, you can recast a lot of model fit in terms of non-centrality. And RMSEA is the average non-centrality per degree of freedom in the metric of the likelihood. So those are the fit indices, and I'm not a fan of any of them.
The latest version of M+ offers three or four primary fit indices. It offers the SRMR, standardized root mean square residual, which makes no parsimony correction at all. Just gets better and better the more paths you jam in there. Root mean square error of approximation, as you mentioned, which does take into account something to do with the complexity of the model. And then the CFI, for example, comparative fit index, which is an example of an incremental fit index that compares against a baseline or a universal ugly house. But the thing that everybody wants is to know how big do these things have to be? And we get back to this p-value like reasoning. And, a number of years ago, 21 years ago now, a paper came out by Hu and Bentler that I think was very well intentioned. And I don't think they overplayed their hand in it at all, but they tried to come up with what would be better cutoff values for these different fit indices. Actually, they took many fit indices and found that some didn't perform well at all, no matter what cutoffs you had, and some performed better. In particular, SRMR and RMSEA and CFI all performed relatively well given specific cutoff values. And people sort of heave this sigh of relief because, as you say, Moses now has a third tablet, and whether that tablet was, courtesy of Bentler-Benet or Hu and Bentler or whomever, people go, oh, thanks, I don't have to do any thinking anymore. God forbid that all three of those indices don't align, and one of them gets out of whack. But I would really like to hear why that whole enterprise makes you a bit uncomfortable. I definitely have some reasons myself, but would you mind just sort of unloading a bit on that?
What we're trying to do is too complicated to just make a binary decision as to whether our model is correct or not. Just to be super clear, as I love the Hu and Bentler work. There's been a ton of really good stuff. Ken Bolin has some very nice papers exploring the role of sample size and the fit indices, and all of the work is very well motivated because despite evidence to the contrary, as I'm not a grumpy old man who just yells at the kids to get off my lawn and slams the door, I'm still trying to understand the extent to which I can instill confidence in that mediating mechanism that I'm estimating within my path model. And the fit indices are a very important step to doing that. Mine is kind of the Smith & Wesson, the gun manufacturer who somebody said a number of years ago is we just make the gun. We don't shoot people. Mm-hmm. And you can respond to that in whatever way you want. Mm-hmm. But I see the fit indices kind of like that, is they represent information and they represent potentially important information. But I've worked with so many people who have had a CFI of 0.89 and want to add a parameter so that it gets to 0.90. Right. So part of it is that kind of motivation. But the other one is there are no universal rules that span all possible models. Mm-hmm. Some models have latent variables in them. Some have latent factors that are well determined, right? Like stronger loadings, weaker loadings, complexity, sample size. We haven't addressed, we can talk a whole episode about non-normality, right? So we have distributional assumptions that go on that. We have all of these things. And to say that you need an RMSEA less than 0.5 is just both philosophically and empirically unsupported. And there's a lot of simulation work out there that shows that for some models, an RMSEA of 0.1 indicates good fit. For some models, an RMSEA of 0.02 indicates extremely poor fit. It goes back to what we were talking about in the last couple of episodes. It depends. So what value indicates good fit? Well, it depends. It depends on all of these other things. And it goes back to that, is statistics cut and dried. This may be the only time in the history of quantitude that I'm going to be able to use my ability and voice skills appropriately is just over the weekend with my daughters. We got a pizza, we got a fire in the fireplace, and we watched Pirates of the Caribbean, which is one of my favorite movies of all time, and arguably one of the best lines out of the movie. The young woman is talking to Captain Barbossa and invokes the pirate code. And in part, he says, the code is more guidelines than actual rules.
According to the code of the Order of the Brethren.
First, your return to shore was not part of our negotiations nor our agreement, so I must do nothing. And secondly, you must be a pirate for the pirate's code to apply, and you're not. And thirdly, the code is more what you'd call guidelines than actual rules. Welcome aboard the Black Pearl, Miss Turner.
I love that. The code is more guidelines than actual rules. And I feel like fit is that, right? There is not a switch that says you're a good person, yes or no, right? Because we become personified in our model, and that we're looking for some observable objective criterion. How I view it, and I teach it this way, is you're like a prosecuting attorney, and you are making a case to the jury as the extent to which you have confidence in your model. And you have a chi-square, and you have incremental fit indices, and you have absolute fit indices, and you have SRMR. But then you also have each dependent variable has an R squared, a variance explained in it. You have significance of each of the parameter estimates. You have our friend modification indices, right? And all of these build a constellation of a multi-dimensional informing of the extent to which you have confidence that the structure you imposed on your system of variables did not knock over the Jenga tower. I feel like you're not after the model that relates your variables together. You're after a model. Because if you never want to do an SEM again, go read Lee and Hirschberger's work on equivalent models. Yeah. And you'll never do an SEM again in your life, because they show that under very common circumstances, there are hundreds of alternative representations of any reasonable model that lead to identical log likelihood values. It's not, stress could cause negative affect, but negative affect could cause stress, and those are alternative. There are reparameterizations of models that are numerically indistinguishable. Yeah. And so if you appreciate that going into it, then to me it becomes a case-based presentation to the jury, that where the jury is the journal article reader. The reader of your article is you're building a case, you're presenting all information, and then you're making a substantively, empirically, theoretically informed determination about the extent to which you believe your model.
Yeah, I agree with all of that, down to the characterization of what modeling is at the end. With regard to the fit indices themselves, one of the things that I've had a few papers that have explored have to do specifically with the role of the quality of the loadings, right? The quality of the measurements that you have. And if you go back to Hu and Bentler and other work, you find that they created scenarios that had loadings around 0.7, 0.8 in all of these models, and that led to particular cutoff recommendations. And if you went back and replicated their entire study using loadings of 0.5 or 0.4, you would come up with entirely different recommendations. And to me, that just speaks to the tenuousness of any recommendation that you can have as a true cutoff value. And so here we are wandering this world. Statistics was supposed to bring order to things. And what you have just said is that we're really a bunch of lawyers. And I agree that we are. I would prefer to say that we're scientists, right? That we are gathering evidence to try to support or refute. We can't forget that. Support or refute a particular system that we have. And the evidence that we gather is not, I think we have to be completely transparent and say, yeah, some of this is really strongly in support of this. Some of this also points to the weakness. I have this local fit information that says maybe there's a part of the model that's not functioning so well, but other information I have show that there's some good stuff going on here. And in fact, if I had made modifications to that part of the model over there, you know what? Inferentially, I wouldn't be reaching any different conclusions. And that brings us back to, your concept of sensitivity analysis and the poking stick. I think that is all perfectly embedded within this process. In the end, we're not, did you make it over a 0.95? Did you make it under a 0.05? It's not like that. This is what I believe, or this is the space of things I believe. Here's some evidence that supports it. And yep, the jury and opposing counsel is going to be able to poke holes in that here and there. But on the whole, it may well move us forward. And then you bring out your poke and stick and say, yes, even if you're right about those things, let me show you what the effect is. So I like everything that you said, right down to the voice I heard from you thinking the poking stick.
It's all poke and stick, right? Mm-hmm. I was on an airplane and watching an episode of The Good Place, and the head demon, they were having a demon conference, and he was talking about needing to innovate, and his example was, did they need to improve their poking sticks?
Humans are worse than ever. We have to innovate. Sure, poking sticks work great, but should those sticks be sharper or hotter? Should they counterintuitively be less hot? Let's begin with slide number 1 of 7,000.
What you're raising that is really, really important, I think, and it's that distinction between global and local fit. Everything that we've been talking about is the fit of your model, right? So we've, again, this 10 variable, mediating system. It's like just an up or down vote of a go, no go. Is that right or not? Mm-hmm. Right. And so I often think about, does your model fit or not? And my answer often is yes.
Mm-hmm.
Right. Because some parts are going to have greater explanatory ability than other parts. I have become a bigger and bigger fan of doing everything we talked about. Chi-square, incremental fit indices, absolute fit indices, SRMR, modification indices, expected change statistics, there are all these things. I routinely now look at the residual covariance matrix. So you can take the observed covariance matrix, the implied, subtract any software package will give these to you. Any software package will standardize these. And what you find in almost any model of any reasonable complexity, parts of the model work well, and there are little parts that maybe don't. And then that's where you pull out the poke and stick. And what I do in my own work and what I try to encourage my students to do, and this has come up in prior episodes, is if you made reasonable changes to the model, would you change your discussion section? If my main focus is parental alcoholism, distress to negative affect, to deviant peer affiliations, to substance use, if that's my core mediating pathway, if I go dink around with other parts of the model, would I make the same substantive conclusions, or does that change in some way? And if that changes in some way, then it's on me to figure out what is the source of that and what do I believe.
Yeah, I think that currently issues of local fit are really underutilized and underexplored in their value. I mean, when you and I talk about looking at the residuals or standardized residuals, whatever we want, that's one way to do it. There's also local fit in terms of parts of the model. When we talk about a model having degrees of freedom, it's often that it's just parts of the model that have the degrees of freedom. There's some parts of the model that are saturated off in their own little areas. So you're never going to get any badness of it coming from them. And so you can even focus on fit in regions of your model. And software doesn't really help you to do that a whole lot. But I'd love to see us to move toward that. On one end, we have the global fit. On the other end, we have the variable relation fit, but then we have these chunks of the models where the badness of fit is really where the degrees of freedom are housed, where the opportunity for badness of fit is. And it would be nice if we did some more stuff to try to A, characterize that, make that, B, make that accessible to the researchers, and C, help people to do exactly what you described, assess the sensitivity of the key results that you have to what's going on in those areas. And inferentially, it just might not make no never mind, right?
Right. And first, I really appreciate you going A, B, and C. They weren't numbers, but they were letters, and that's good.
Okay.
But second, you're raising a whole nother thing that's totally cool, which is that notion of parts of the model are saturated, but parts are not. And so it's not uncommon to see in literature a very complicated latent variable model, right? Where you have 6 latent factors, multiple indicators, and maybe 200 degrees of freedom. That's not uncommon. You see 150 degrees of freedom, these ridiculous numbers of degrees of freedom. But at the latent variable model, it's saturated. The structure is saturated.
That's right.
Again, we've talked about flexing in front of your mirror, and now it's flexing in front of your degree of freedom mirror, and said, well, look at how courageous I am. I have 200 restrictions on my model, but your latent variable space is saturated.
Yep. Just means you had a lot of indicators.
It means you had a lot, maybe too many indicators. Okay, it always brings us back to the so what. So what do we do? So given this, what is your exit strategy? What do you recommend in your own work, but also as you work with others?
Some of the thoughts that have accumulated over our conversation. One is that the Jenga tower represents not just our models, but it actually represents fit indices as a domain. People like to think of them as being these rule systems, and they're not. Any one of the fit indices can topple, and it may or may not be telling us about the model. So I wanted to say, and I think we have a habit of doing this now, is doing an episode where it seems like maybe we're going to bring some great clarity and order and tell people, here are the 9 steps that you have to do something like this properly. And really what we do is we wander the space and tell people about all the landmines and all the problems that are out there. This is one of those areas. And, so what do I do with people? I try to talk about fit as gathering evidence and understanding what each of those fit indices is telling you. I think it's a very telling thing when you have, let's just say, a decent SRMR, a decent RMSEA, and a low CFI. What do I do with that? We don't just go, oh crap, 2 out of 3. We go, whoa, why? Why do you have a low CFI? What is it about? How do CFIs work? What might that be? Does that just mean that you generally have maybe weak relations in your data? And so your model is doing a great job of explaining the weak relations in your data. And so you get good SRMR, you get good RMSEA, but your CFI's low. And that's just because, your house isn't really that much better than the house next door. I try to tell people that it's partially about the numbers, but it's really about what they're telling you collectively. And each one is looking at your model from a different angle. And we combine that with the diagnostic information that we get out of residuals, modification indices, which have some relation to those residuals, and then to the extent that we can, understanding the more functional regions of our model and dysfunctional regions of our model. But I really can't enumerate this any better than its principled argument, a principled argument that you have to be willing to fail in making that argument. And at the end of the day, maybe you do fail and your model doesn't survive. And that's in the interest of science. That's what should happen, I would say. Or maybe at the end of the day, the jury says, yes, congratulations, you've convinced us. You always, always have to remember that you have not just made a case for this model. Your model at best remains one plausible explanation of what could be going on. And it's got 192 friends coming along with it that are those equivalent models that you might be able to discard because some of them don't make theoretical sense. But you cannot forget that those are always in the background. The best you can hope for is that your model stays as one tenable explanation until the next challenge that it faces.
Yep, I couldn't agree more. And one of my heroes is Karl Popper, who decades ago advocated strong falsificationism. And I don't think strong falsificationism applies well in the social sciences, behavioral sciences, because there's not a go, no-go decision. But he's this intellectual goose that, again, paraphrasing something he said, is that we have to put our theories in mortal danger on a daily basis. And from the physical sciences, kind of the poster child of that was Einstein's gravitational lens, right? So he hypothesized that light, because it was part particle, would be impacted by gravity. And he has all my quotes are paraphrased, I don't remember any of these, but at some point he said, we were not currently able to measure whether light was affected by gravity, but at some point he was confident that it would be measurable, and he predicted that it would be shifted by this amount, and if it was not, then this aspect of his theory was incorrect. And then some 10 or 20 years later, that they were able to do in a full solar eclipse, and the light from a star behind the sun was shifted precisely what was predicted by theory. And so we can't play that card. I love Kuhn, right? The structure of scientific revolutions. The social sciences fails when we try to draw too many analogies from the physical sciences, because there aren't these laws, right? There's Kuhn talks about Boyle's law, and it's like, all right, well, we don't have Boyle's law, right? We don't have a gravitational lens. And so that's why I really like how you put it is a model. It is a representation. How I view it is remembering that everything we do is just a pebble that when we're done, we toss it in the pile of science, right? No model stands alone and says, stress and negative affect mediate parental alcoholism on adolescent substance use. This is one empirical point in the broader argument that we're making. You're right, we're not lawyers, right? And we are scientists, but we are making a reasoned, empirically supported argument to the reader to justify the conclusions that we're drawing in our paper. And the beauty about our field is I might read your argument and disagree with it.
Yep.
But I disagree with it based on full information. Bring all of these things to bear. And then, we talked in a prior episode about how one of the most important words in science is however. Maybe a close second is in sum. In sum, this evidence, blah, 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 is supporting, but future work is needed to better understand the complexities of these relations. Technically, in sum is 2 words, right? Wait, you mean in all these years when I've said in some?
There's a space in there.
Damn.
I don't know if you knew that. I know.
I got in a huge argument when my daughter was 5 years old because she said roommate was 2 words. It was Roo and mate. And she said, Dad, sound it out. It's roommate. So yes, in some. On that point.
Yes. Well, I hope that we've wandered the space usefully of assessing fit and thinking about fit and understanding why you can't really nail it down, but it doesn't mean that you should give up the endeavor. It just means you should think about this as an evidentiary process. And I hope that's been useful for folks.
I never even think about giving up the endeavor. I think this is the fun part. Right? Is what we're trying to do is hard. It is hard to do. And I think it's a wonderful, engaging challenge of what we do is to say, how do we take a larger amount of information and distill it down to a smaller amount of information while retaining fidelity to the observed data and learn something that we didn't know before? And people give us money to do this.
Wait, you get money?
Not a lot.
Oh, okay.
Anyway, thank you everyone for your time.
Yeah.
We always appreciate it. We hope it has been of some use, and we will talk to you again next week.
And don't forget to submit a limerick. If you have a limerick, please, please, please make sure that you submit it through the multitude of ways that we have, that we've already noted. Anything else? Are we good?
Take care.
All right. Thanks, everybody. Take care. Bye-bye. Be sure to check us out on iTunes, Spotify, or whatever platform you get your other clearly less favorite podcasts, and leave us a review. And be sure to tell your friends. Oh, also, check us out on Twitter, where our handle is @QuantitudePod. You can also visit our website, quantitudethepodcast.org, to check out previous episodes and other really cool stuff. You've been listening to Quantitude, the podcast clinically proven to help you cast doubt on clinical proof. Wait. Today's episode has been sponsored by Base 2, allowing guys like us to say we're a total 10. By the phrase data are, because if you say data is, we really can't be held accountable for our actions. And by the mode, because it just wants a little love. Is that so wrong? This is most definitely not NPR.